Gilad's discussion session. Gilad has to take a plane in the afternoon, and he was kind enough to offer this discussion session. Probably he's going to talk a little bit before some topics, and then we open for discussion. So I hope you have many questions.
Yeah, so I apologize because in retrospect, I think that the way we should have handled it, so this is on me, is first I should have showed you the relaxation, let you digest it, and then talk about all the other options, because the relaxation is like a toy model that shows you how the scanning is working, the presence of the inflation, and all the concepts that we are describing will become more concrete. But I start from the general thing, and then we went to the specific, and we didn't have time, I think, to really dwell on that. But it is what it is. So you have everything in the slides. You can follow this. You have the references. So what I will try to do today, so I will just show you some picture about how the relaxation works, and then we're going to switch to the phenomenology because I still want to tell you about the precision front, the two main concepts. They're looking at equivalence principle constraint and also related to quantum sensor searches for dark matter. Okay, so here is our relaxation. I just remind you that we start with the generic potential. You see here I don't even bother to write the cosine with the big F. I just expand it, in this case, quadratically. You can also expand it linearly. The point is that the frequency here is so huge that it behaves as if it's just have a linear coupling. So it's just slow rolling here, okay? And there is the critical point here where the mass, or the mass square of the Higgs, is 0. So at this region of parameter space, we have electroweak symmetry breaking. And here, when it starts, we are in a symmetric phase. So you see that this is the Higgs potential, okay? So now it rolls. It passes through the critical point. Now we have electroweak symmetry breaking. But at the beginning, this is very small. So the invariant mass, even if it's negative and you have electroweak symmetry breaking, the wave is still tiny. So the back reaction term still is not switched on. So you see the wiggles here are still very small, but now they're growing. And they're growing in such a way that suddenly there's a minimum. And because the relaxation is very slow rolling, the first time it sees minimum, so V prime equals 0, it will stop there. And here's the back reaction. This is slightly different notation. Mu b squared is what I called yesterday small m squared. And you see this is the small f. Okay, so the whole formula, this is what I derive on the board. And you see the most important thing is the weird scaling, that the electroweak scale over the cutoff requires very large hierarchy between small f and big F because it goes like the fourth root. So that's the problem of the relaxation, but you can solve it with the clockwork. I'm not going to cover it, but you can read it. And the other thing that I'm not going to cover is the cosmology. So there are various bounds on this relaxation framework. Already yesterday, people asked me about inflation. So you see, we must assume that the contribution of the potential from the relaxation to the expansion of the universe will be very small compared to Hubble. So this is this bound. And here is the bounds of classical versus quantum that we derived 2 lectures ago. And you combine them together, and you get roughly that lambda needs to be smaller than 10 to the 8 or 10 to the 9 GeV. This is why basically basically when we put the power counting, I told you I took 10 to the 9 GeV. And the last thing that is interesting is that the relaxation needs a lot of time to scan the parameter space. That was the question that was raised by the person who just entered the room. So in order indeed to get from here, in order to get from the region where maybe you see it here, from the region where the mass is negative to positive, switching from positive to negative, then you need to scan a lot of parameter space, and that requires a lot of e-folds. So the inflaton needs to slowly rolls and cover big range of parameter space, and that is leading to an interesting bound on the number of e-folds. I think there was too much attention given to that bound, because what you see is that the scaling of the number of e-folds, so here n is the number of e-folds, goes like the cutoff to the 10th power. So if it's 100 TeV, if the cutoff is 100 TeV, which is not M Planck, we never get to M Planck, but 100 TeV is already far, far away such that there's no way to measure it even if you will have FCC HH, okay, 100 TeV is beyond any reach of any collider, any future collider, even in the next 50 years. So you see that at 100 TeV cutoff, you still have now one E-fold. But if you go to the absolute maximum, which is roughly, so we are talking about, let's say, 10 to the 8 GeV. So if you go to 10 to the 5 TeV, then you see that you need a huge number of E-folds because it's scale like lambda to the 10. And then you'll have a very non-trivial cosmology because you need the inflaton to cover exponential number of E-folds, and that's very weird. But you don't have to insist on that. And I think people ignored, I don't think it appears in any paper, but the expert knows this. This scaling lambda to the 10 suggests that the E-folding problem is not a very serious one. Okay, now we switch to relaxation phenomenology. And what we saw, because of the fact that the relaxation stops roughly at order 1 phase, or more precisely pi over 2, if you're more sophisticated, then you know that there's mixing with the Higgs. And this related to the fact that you have CP violation. And it means that the relaxation is very, very peculiar creature. It started as an axion, so it has axion coupling. But also, it has, because of the mixing with the Higgs, it has also scalar coupling to all the particle in nature. So this makes it, the phenomenology of this very interesting. So very roughly, you can look at the, if you wish, parameter space of the relaxation in the axis of the mixing sinus theta h phi. That's the mixing with the Higgs, and as a function of its mass. And there's a region where it is fine-tuned, literally fine-tuned. So this is true fine-tuning. So we don't want naively to be above this line. I told you yesterday that it is even naturally or sensibly in the sense of my lecture. Okay, so it's unnatural, but in a sensible way, it's actually able to pass this line, which looks like a fine-tuned scalar, but it's not. And there's also a smaller value where the cutoff is the minimal. So this is the allowed parameter space. And now if we want to look for this, so this is the parameter space of this theory. So this is sinus theta of the Higgs between order 1 all the way down to 10 to the minus 30. And this is the mass of the relaxation, which is around, if you wish, MEV. So here it's GeV already. This is in units of EV. So here it's GeV. So here you can look for it at the energy front. And then you can look for, at smaller masses, you can look for this with astrophysics or with the luminosity frontier. And then once you pass roughly EV and below, all of this region is covered either by cosmology or by precision tests. Okay? All of this region can be covered by what I call quantum sensor or quantum science. And if you are thinking about the relaxation in general, because of the parameters being technically natural, then it's interesting that we don't have, if you wish, favor for this region or that region. And that's very interesting that nowadays quantum science, who is an exponential explosion development, will cover all of this region. And this is why I wanted to cover this. The last thing that I want to mention is that also it's quite easy to see that the relaxation can give you a solution, can be a dark matter candidate. Ultralight relaxation will oscillate around the minimum and will become also a dark matter candidate. And this is the region of where it works as a dark matter. Yes?
In this very high mass range, is this still classical evolution?
Yes. All of this region between these two lines, all the bounds that I derived in the previous slides hold. So it's still classical. Yes?
So if the relaxation and if the mixes with the Higgs, if I understand correctly, right? And so if you say it's a dark matter candidate, wouldn't you inherit all the decays of the Higgs? Or if it's too light for that?
No, yeah, so it's very, very light. So here, the mass of the relaxation is 10 to the minus 10 EV, let's say. And it has coupling of the photons because the Higgs coupling to photons, right? There's a H gamma-gamma coupling. So there's also relaxation gamma-gamma coupling. But the rate goes like m cube over the coupling. So it's a super tiny rate. So it's stable. Similar to the axion being stable, even though it has coupling to photons.
So the axion, because of being so light, it's basically stable. Or it is
Yeah, its lifetime is super duper long, yes.
If it's coupling to the Higgs, then shouldn't there be bounds from like invisible Higgs decays?
Absolutely. So, yes, so we have a whole paper just on looking at that. And the best way to search for the relaxion, if it's heavy, is either indeed through the Higgs decay to relaxion, but the relaxion in this region decay actually, so it's not invisible because it mixes with the Higgs, so it couples to the same way with Higgs, but you can actually identify, depending on the mass, the final states. And also, remember, Christoph in his colloquium yesterday showed you that if you will have ever FCC-EE, there will be a Terra Z machine, a machine which will produce E plus E minus Z on shell, 10 to the 12 Z's. And that, through a process which looks like that, so we have E plus E minus, goes to Z star, and the Z star emit a Higgs which mixes with the relaxion. And here we have the Z. Through this process, if you can produce many, many Z's, you can search for the relaxion in a very efficient way, a little bit going off shell. And that's giving you the strongest constraint on the relaxion coupling. I don't think I have here the plots, because I wanted to talk about quantum sensors and not about the energy frontier. Yes?
Yes, just a quick follow-up question. So if I want to make the relaxion heavier than electron mass, let's say I just have to make the mixing really small. Is it fine to do that?
So naively, without looking at the relaxation effect, which I did not explain, then very roughly the mass of the relaxion squared is just given by the back reaction mass, m squared, times v squared divided by f squared. Okay? So it depends on the value of small f and m. That's what is going to give you the mass of the relaxion. Okay? And what you see in this plot, all of this region is consistent with all of the requirement of the relaxion, cosmological requirement, and the naturalness. So here it has to be between these two green lines. Okay? By the way, here we already include this relaxion phenomena. So you see, this is the naturalness line, but the relaxion lives well above. This is logarithmic. Yeah? So you can get a relaxion which mixes with mixing strength, which is 3 or 4 order of magnitudes above what will be the naturalness thing. So if you are looking at a Lagrangian, which Higgs portal Lagrangian, you just write something like m squared Higgs squared minus m squared relaxion phi squared. And then you add the trilinear coupling, phi h dagger h. And here let's call this coupling maybe mu. Then you can derive a naturalness bound of the size of mu because you have a contribution to the, let's say, to the relaxion mass, which looks like that. So this is this mu phi h. This will give you contribution to the relaxion mass. And what is so beautiful in this relaxion idea is that the relaxion itself makes its mass unnatural, but in a sensible way. That's the theme of my lectures. And it makes this mu unnaturally big, effectively. So you can go well above this naturalness line. So if you see a Higgs portal, and there are many search for Higgs portal, this is a generic model. It's called just Higgs portal. And you see that its coupling is unnaturally big. Maybe that will be a sign for that if it's in the MEV range. OK, let me move on. All this is the relaxion. So this is about how it sees dark matter. So we're not going to cover all this. But now what I want to tell you is that how do we search for this when it's ultralight? OK, there's a big parameter space where this m and this m is small, this f is big, and the relaxion is light. And we want to search for this. So the most important search, we already mentioned, is related to equivalence principle test. So first of all, let's look at the Lagrangian. I just highlight two coupling of the relaxion. So relaxion mixes with the Higgs. Higgs couples to electron. So there will be some coupling, effective coupling of the relaxion to the electron. So I'm writing in this way, dimensionless coupling, the relaxion in units of M Planck times ME E bar E. So it's easy to compare it to the relaxion phenomenology. And also we know that the Higgs couples to the gluon, so therefore the relaxion will couple to the gluon. And in general, the couplings to the gluon should be the biggest, okay? Because if you look at the low energy limit, then the Higgs has big coupling to the gluons, and the gluons becoming the hadrons. So it means that the relaxion will couple to the hadrons. That's the most important coupling of that. In general, the coupling to gluon is very important when you think about scalar dark matter. And also, as I'll show at the end of this discussion, also for axion, as we recently obtained. So if you are searching for that phenomenology, maybe the best bet is to understand what are the bounds on something which couples to the hadrons, okay? Because the gluons at low energy will be interpolated into proton, neutron, pion, etc. So this is what you should focus on. So how the equivalence principle bound work? To make it simple, let's just assume that we have only the coupling to the electrons, DME. And by the way, I think I have a typo here because there should be ME, okay? I defined it, this coupling with ME, so I'm missing an ME I see here. So if we look at the non-relativistic Lagrangian of the electrons, I just have the mass, the bare mass, and plus the correction for the mass. So this term basically is just giving us correction to the mass, okay? If phi is a constant, I can just redefine the mass of the electron as the sum of this term plus the bare mass of the electron. Okay, that's very easy. And stop me if you don't understand, but I think that this is simple enough. So now I can write the Euler-Lagrange equation, and I find that the acceleration related to the fact that we have a relaxion background is just proportional to the discoupling times phi prime. What do I mean? Just to make it maybe more clear, let's have some example in mind. So let's suppose that this is the Earth, okay? And here I have many, many electrons. And I have this coupling between the electron and the relaxion. Okay, so this will be source for the relaxion. And when I solve the equation of motion for this scalar, because it's very, very light, I will get an effective potential, which will be proportional to the full charge of the Earth, if it's very light and it sees the whole Earth by Gauss law, which will give result in the effective coupling here. Let's call it alpha E times e to the minus mr. M is the mass of the relaxion over R. In the limit where the relaxion is massless, this is just a massless scalar, which is just going to intermediate. So when ME goes to 0, of course, when M phi goes to 0, of course, this will be just 1 over R potential. Okay? So that means that if I now introduce a test mass somewhere here, so here I have a radial potential, and now I put a test mass here, which has some electrons in it, then this test mass will be subject to a potential which is given roughly by that, and the force, the acceleration, will be proportional to the derivative of phi at the point of the test particle. And you can actually do this, you can do this more precisely. If you put an atom, then you know exactly how the mass of the atom is related to the mass of the constituent. So you have the nuclear part of the contribution to the mass of the atom, and then you have the number of the electron in that atom, and then you can add the binding energy. So all of this will be related to the effective potential seized by this test mass. This test mass typically is some element, okay? Gold or platinum, something like that, some heavy element. And we can just redefine this effect as writing it as the total mass of the atom times some a parameter which is called usually alpha. Is it alpha or A? Maybe it's it should be alpha. Okay? So this basically alpha is just related to the derivative of phi, so that's the force, times d log m d phi, which is give us what is the sensitivity because of the coupling of the electron. And you can put a g Newton or square root of g Newton just for normalization. Why it is useful? Because the total acceleration will be, we can write it, the total acceleration can be given as the Newton coupling times the test mass times the alpha variable defined as here, times the m, the mass of the total Earth, times its effective coupling alpha divided by r squared. Okay? Why is this useful? Because it looks exactly like the Newton acceleration, but with some parameter alpha, which are function of how the scalar couples to the constituents. Okay? And yes?
The nuclear mass you're getting from the gluon coupling?
Yes, yes. But for now, I said I'm going to think just about a model just to simplify that I couple only to the electron. So effectively, this would not be a function of the relaxation. But in general, yes, that's the most important parameter. Good. Yes, Felix?
And so, in the difference in the Higgs, you have to work in the background with phi.
Again?
In contrast to the Higgs,
Yes.
the only difference is that you're working in the background with non-vanishing phi.
You mean if it's dark matter or what?
No, I mean, I have the coupling of the Higgs as a proportional to mass, but in principle also gives me a power potential between the electrons.
For the Higgs. But the Higgs is super heavy, so it will be short distance.
Yes.
So here I'll have MH. Yeah, in principle, if I can do this experiment over distances of 10 to the minus 18 meter, then I can do, but this is so small. Here I'm talking about a case where I outside of the Earth, so I need M phi to be very small. In fact, I will think about inverse M, which is be of the order of 10 to the 5 kilometer, which corresponds roughly to 10 to the minus 15 EV. So I'm looking at really, really light relaxation here.
What do you mean the dark matter part?
No, this is independent of dark matter.
Okay. I mean, your first line is dark matter scalar, not just a scalar. Right?
Yeah, because later I will, in the next 2 slides, I will introduce the dark matter searcher. But right now, you're right. It has nothing to do with dark matter. It's very generic search. So, yes. You have to repeat it.
Why do you use platinum as a material?
I will say a few words about it. You need something that you can, something which is very, very clean, very pure, and that it doesn't leak, because we're going later to put it on a satellite which is orbiting the Earth, and you want to control this mass very precisely. So typically, they put very heavy material that is very pure. Remember, I want to calculate these alpha parameters, and to calculate the alpha parameters, I need to know exactly what is the composition. Great. So now what we find is that with this formula, if we know how to calculate this alpha for typical coupling, then we get a formula that up to these alphas, it looks exactly like gravity. The only difference is that this alpha, they depends on the exact coupling that I put for the relaxation. For example, the relaxation, we know its dominant coupling is the gluon, and according to the mixing with the Higgs. But if I know the decomposition, then I know exactly how to calculate this. And now there's a very important variable which is called the Etvosh parameter, which is just measuring the differential accelerations of 2 bodies. So that will lead to the most precise measurement done by human beings. So if you never heard about this, then it's important that you know. So instead of having 1 test particle, let me actually put 2 test particles. Let's say the yellow and the blue. And this has one decomposition, and this one has another decomposition, so it should be in blue. Now, gravity, of course, as we know from the days of Galileo, is universal. The inertial acceleration is the same as the gravitational acceleration, right? The masses are the forces are the same. So if I just drop them, they will have, and they are free, they will have exactly the same acceleration. But if I have something like the relaxion, or in general scalar, that doesn't couple to everything with the same strength as gravity, there will be some differential acceleration generated by the difference between the alpha A and alpha B that we defined before. So if I look at the delta A over A, it's easily calculated because I have the same gravitational force downstairs, so everything will cancel apart from the alpha. Alpha Earth is common to both of them because both of them are subject to the force exerted by the Earth. And then I'm just left with the difference between the alpha A and alpha B. And basically, alpha A and alpha B can be just related to what we call the dilatonic charge, which is d log the mass, d log phi, which is dq. So basically, all that I need to give you for specific elements, what are the dilatonic charges? And you can calculate phi prime. And you can, from this, you can actually extract the acceleration. So now there's an amazing experiment which is called microscope. It's just more or less equal to what you see here. It's a satellite. Of course, I'm simplifying, but it's a satellite which is traveling 700 kilometers, circling the Earth. This mission was, I think, sent to space in 2016. And these two masses are floating, and the satellite is free fall. So by Einstein, right, if all of them are free falling, then they should be exactly the same frame. You shouldn't see any motion, any relative motion. All three bodies are basically free falling. But if we have some force which violate the equivalence principle, we start seeing a differential acceleration resulting with the fact that basically one of these two masses will hit the wall of the satellite, and that's it. And because it's flying for 6 years now and everything is still okay, then it means that we can have an amazing bound on...
Actually, recently they
just 2 weeks ago.
I saw this on the screen in the subway on the way here.
I see.
2 days ago.
Yes, so just 2 weeks after 5 years.
The subway in St. Paul was an equivalent test principle.
On the subway it was announced.
And the subway on the screen. But,
So they have good tests in Sao Paulo.
Very,
Because that's the most precise measurement done by humans. So.
No, I mean, they were just announcing the news, and this was in the news. So.
Yeah, so the bound is so strong that we see it here. So this is for the DME, okay, this is the EP bound. And for the DG, this is the EP bound. And you see that it's much stronger. Remember when we discussed quality, it's much stronger than 1. Okay? Great, so that's the first way to test this kind of theories. Yes?
Is the alpha sign known?
What's that?
Is the sign of alpha known?
The sign of alpha,
The change in the mass with respect to
yeah. You can calculate in specific theories.
the positive and negative.
You ask whether the force could be negative. If you have one coupling, then it will be proportional to the square of the coupling. Probably not, but if you have several, yes, I think you can get both. In fact, in general, what we showed some times ago is that you can, for one specific, okay, you know it's complicated. We can discuss it later. But one specific measurement is telling you about linear combination of the coupling. So you need more than one in order to constrain dark matter theory. Okay. So now let's talk about the second way to constrain this. Now I'm going to promote my relaxion to dark matter. And that leads to something which is, I think, very, very interesting. So if the relaxion is dark matter, it means that it's oscillate with time. You'll see this in Raphael's lecture. You didn't discuss yet axion dark matter. But you'll see that it's oscillate with time. Okay? Basically, what happens when you have ultralight dark matter, it means that we are all living in the background of a scalar or axion. And this axion all the time oscillates with time. The amplitude is related to the dark matter density. And the frequency of oscillation is related to its mass. So we are now in a background, if this is the solution for the dark matter problem, we are living in a background of some field which with amplitude change with time. Okay, that's fine. But what is interesting, if this field mixes with the Higgs, so axion wouldn't do this, but the relaxion we know does it. If this field mixes with the Higgs, what does it mean? It means that because the Higgs gives masses to particles, it means that all the masses of fundamental particles change with time. For example, the electron mass all the time oscillates. Alpha, the coupling constant of QED, also change with time all the time because we have Higgs FF coupling. So Higgs mixes with the relaxion. So alpha also oscillates with time. Lambda QCD oscillates with time. Everything is vibrating. And since if ME oscillates with time, it means that the size of the atom changes with time. It means that the Rydberg, the difference in energies, change with time. So that's quite nice. It's something that we should see in principle. Okay, now the question is how to see it. So first of all, just to give you a feeling before I quote an experimental result, we can just estimate what is the change related to, let's say, hydrogen atom energy levels. And the actual experiments are not that far from what I will show you here. So we know that the Rydberg constant goes like ME times alpha squared times 1 over 2n squared. So let me assume that I'm looking just as a toy model. It's not exactly like that, but it's fairly close. So here is my hydrogen atom. And here is my 1s state. And here is my 2s state. Maybe 2p, at least to be slightly more realistic. And I'm looking at electron, which move between the 2p and 1s. Okay? Then, of course, if you look at regular quantum mechanics, then the energy of the photons emitted in this case will be exactly what's written here, some 3/4 m alpha squared times half. But in a theory where this is subject also to dark matter, then you see that there's a component here proportional to the dark matter density and decoupling, which oscillates with time. So the difference in energy level all the time oscillates with time. So you can actually try to search for such a thing. And how do they do this? They do this with something which calls clocks, atomic clocks. How atomic clocks works, let's keep this example. What happened is that instead of working in energy eigenstate of the atom, they put what they call pi poles. So they create a state, let's say we call it like that, states nu, which is a linear combination of these two eigenstates. So 1s plus usually I, never mind y right now, times 2p. And maybe there's 1 over square root of 2 for normalization. Now, if my initial state is like that, I manipulate my atom and I create a initial state, which is like that. This is, of course, not eigenstate of the Hamiltonian. So what happened to it? It starts oscillate with time, right? You solve the Schrödinger equation. You all did this in your undergrad. It oscillates with time with a frequency which is equal to the energy levels difference between these two. That will be the solution. So this oscillator, in principle, if you don't have any background effects, if it's in a very, very quiet system, it will continue to oscillate forever. It will be the most precise, if you wish, pendulum experiment. And this is why atomic clocks are so amazing. Okay? This is why they get super crazy precision. And this is what I'm describing here. In the presence of dark matter, what happens, apart from this oscillation, because all I'm going to calculate is e to the power IHT, then I also have the dark matter oscillate and creating a phase difference in the oscillation frequency. And if I do a measurement now, without the dark matter, I can calculate exactly what is the probability to find the electron in 1s in 2p. But with the dark matter, I will get a small deviation from that. And now these systems are so precise, they can do this measurement to precision of 1 in 10 to the 18. Actually, now there's already one experiment which reached 1 in 10 to the 19. Okay? So that means that it will result in super strong bounds on the coupling of dark matter, let's say in this case for M electron. Okay. And the last thing that I want to cover, and then we can have a free discussion if you have questions, is maybe the most amazing experiments that not many of you heard of. So I'm very happy that I have a chance to tell you about. That's related to nuclear clock. So let me start first with the motivation. We already hinted that it's very important to search for scalar which couples to gluons. We gave example, if you have something which mixes with the Higgs couplings to gluon is huge. So that is motivated. There are also models of dilaton dark matter. And also the dilaton has very big coupling to the gluon because of the anomaly, basically because of the running of the QCD constant. And I will argue at the end that there's also another important implication of that. The QCD axions also can be searched for when you are using nuclear clock. Even though you would think that the axion has nothing to do with the energy level difference, but the second order in the axion coupling, in the axion field, then you also modifying the hadronic energy levels. I will show you in the next slide will be the very last one. So now, however, it's very hard to search with this technology, search for the couplings to the gluons. The reason is that the energy levels are as to leading order are function just of ME alpha squared, right, Rydberg. So it has no dependence on the nuclear part. So how am I going to search for this coupling? You see this coupling? How am I going to search with this if the only thing which oscillates is lambda QCD or the alpha S, the strong coupling constant? If this is what oscillates, how am I going to search for this with clock? It's very hard. And one way is just to remember that when I write here, when I'm assuming that Rydberg is ME alpha squared, this is not exactly correct because here, when I solve the hydrogen atom, remember I'm solving in the center of mass. So what appears here is really the reduced mass. So to leading order in the infinite mass of the nucleus, this is indeed just ME, but there is a small correction where the thing which appears here is effective electron mass, which is given by ME times 1 plus ME over M nucleus. So if M nucleus oscillates because of the fact that lambda QCD oscillates, then I will have some sensitivity here. But this is very small because it's screened by a small factor, ME over MN, which for heavy nucleus is 10 to the minus 5. So I have a very weak sensitivity to oscillation of the hadronic parameters. One interesting thing that we are about to pose is that you can look instead of the oscillation of the mass of the nucleus, which is suppressed, there's another effect. The charge radius of the nucleus oscillates, so you can search for how the energy levels depend on the oscillation of the charge radius. That's a new concept, and it will lead to a strong bound. But here I'm going to now go back to the most amazing experiment in this frontier. It's still not ready yet, but when it will come out in roughly 1 minute of running, you will improve the bounds on this kind of physics by 10 order of magnitudes. So this is, I think, something which is unprecedented. So why is that? There is one state out of all the nuclear physics, talking about fine-tuning, there's one isotope, which is isotope of thorium-229, where if you look at the energy levels of this system, instead of having a mass splitting of MEV, so we know that nuclear physics is very rich and we have nuclear excitation, but typically the difference in energy between one nuclear and another nuclear excitation between, say, N and N star is of the order of MEV or more. But there is one very special isotope, this thorium-229, that the splitting between the excited state and the ground state of this nuclear is 8 EV. So there's almost 10 to the 5 fine-tuning there. what is the fine-tuning? There's the nuclear energy, and there's the QED repulsive force, and they conspire for this specific system to cancel. This is order MeV, this is order MeV, but the difference, which is the energy levels that you actually measure, is of the order of ATV. That is something crazy, and people are trying to measure very precisely this energy difference, because then they can apply exactly the same principle and create a nuclear clock where the two, the excited and the ground state of the nucleus are superimposed like that. And it will be a nuclear transition which will oscillate forever. Now, why is this so spectacular? Because let's do exactly the same thing that we do here. We want to measure how the energy level oscillates because of the coupling to gluon. So we want to calculate delta E over E. So let's assume that now I switch on only the coupling to gluon and not the coupling to electron, or the coupling to electron is negligible here. So only the nuclear part of the energy level contribution oscillates with time. Okay, so I want to look at E nu T minus EQED. This is constant, divided by the 8 EV, the nuclear clock energy. Okay, so I'm calculating delta E nu because EQED is constant with time, so only this part oscillates with time. And then I put in back the dark matter part. Okay, so this is the dark matter coupling to the nucleus, times E nu divided by the E nu clock. But this, we said, is of the order of 10 to the 5. So every small oscillation of the dark matter is now it's amplified, sorry, by factor 10 to the 5. So if I build nuclear clock with precision 1 in 10 to the 18, or 1 in 10 to the 19, which is currently state of the art, this will be amplified by factor of 10 to the 5, resulting with a bound which is bigger by 10 order of magnitudes. And the impact of that, instead of showing this for scalar, I want to show you what it will do for QCD axion. So here is 1 over F related to QCD axion searches, and this is the mass. And here is the star cooling bound, roughly 10 to the 9 GeV for the QCD axion coupling. And you see, because of the fact that the QCD axion has quadratic in QCD, the axion has quadratic coupling to the energy level, it will also create effect that you can search for oscillation in nuclear clock, and this result with this bound from running the nuclear clock, so it will cover all this region of parameter space which is uncovered. It's still not going to be sensitive to the QCD axion line, but it's still going to be the stronger bounds, much better than magnetometers, Casper, etc. And this is why it is so amazing. All right, so now we'll conclude, and then we'll see if there are questions. All right, so we started this set of lectures just talking about that we are living in a constant state of bewilderment, of puzzlement, because we have the strong observation for beyond the standard model, but we need to compare them with the vast predictive range. So this anomalous observation don't relate to a specific scale. So we introduced 2 soft principles to try to help us think about viable explanation of these anomalies, and this is related to naturalness and the quality problem. Then, inspired by Weinberg, we introduced the solution of the cosmological constant, and we saw that maybe there's another approach to solving the naturalness problem, and this is related to use cosmology to address this problem. Okay, so instead of adding TeV new physics, maybe the cosmology, like the relaxation and other things that we discuss, will help us to solve this problem, and this leads to radically different phenomenology. Instead of looking for TeV physics, suddenly we need to look for 10 to the minus 15 EV scalar through maybe oscillation of fundamental constants. So it's totally different type of phenomenology, or through equivalence principle. And we see that now the quantum science is in a state of exponential growing. So the precision is improving every year by at least order of magnitude, which is amazing. And this is why this is an exciting front. So thank you very much.
sure there are many questions. So Gustavo will take this side, I take this side. Okay, I go first. I got first.
Okay. So when you answer this question, I think I misunderstood your answer. You said that the contribution from this effect to this alpha parameter can be both positive and negative? So you can have an effective mass that is an effective induced mass that is both signs?
Yeah, I think that there's no...
I mean, Yukawa, it's only attractive, isn't it?
What's that?
This is a Yukawa-like, no?
Yeah, this is Yukawa, so...
Isn't Yukawa only attractive? Am I misremembering my QFT1?
But this is if you have electron to electron. So what I answer to Felix is that if you have several couplings, suppose that you have electron, I don't know, electron alpha gluon with all kind of different admixtures, then I'm not sure that it has to be positive.
Okay, yeah, the gluon can probably be, yeah, okay.
So this is, with one coupling, I think I agree with you, it has to be attractive.
I mean, if it's, even if it's more coupling, but if it's a bunch of Yukawas, they all need to have the same sign, don't they?
No, I don't think so. We can think about it.
Okay.
No, if I have each, so the coupling is free. What makes it attractive is that when I square it, it's positive, right?
Yeah.
I can do positive or negative coupling. It doesn't matter. The square of it is positive. But let's suppose, I'm thinking now loudly, suppose I have alpha to the electron, beta to alpha, to the FF, gamma to gluons, and I change with the sign, and then I square it. I'm not sure that it's positive definite. You can think about it.
Okay, I'll think about it.
Because it's not Earth. I have one decomposition for the Earth, another composition, let's say, for the platinum. So it's not obvious to me that it needs to be positive, but we can think about it.
Yeah, I was wondering, when you showed the coupling to gluons, there was a factor of beta G appearing. Is this just a convention, or is there any physics reason behind it?
Yeah, good thing. So you are seeing all the stuff that I was hiding, and I'm happy for that. Yeah, so when I write the coupling to gluons, it of course has a very strong scale dependence, right? Because alpha S runs like crazy. So what do I mean that I have this coupling? So there's a way to write it in a covariant way. If you put in the beta function and the gluon, then this combination is scale invariant. So I know how to relate it from one scale to another. Okay?
It's like the scale anomaly, basically.
It's exactly, this is coming from Dilaton theories. Exactly.
So I have a slightly general and maybe a bit naive question. You say that the kind of oscillation between energy levels, it's like goes on forever. So for me, it's a bit puzzling because, you know, I'm thinking about perpetuum mobile and so on, and if it's radiating, it feels like a bit like that, but maybe because it's microscopic, I don't know. Maybe it's different.
Yeah, so that's an interesting question. First of all, if it's oscillate, then on average, the work done by the dark matter is 0. So you don't need to, once you start this oscillator, like pendulum, right? Once you start it, it's oscillate forever. But we are doing now a project which I think just for fun, okay? And please don't tell anyone. But the idea is that, okay, you have a pendulum. In principle, if you couple it to a spring, then when you go down, the spring will be stretched and then it will bring back the system. But if the spring is now coupled to something, you can actually crop the energy from the dark matter to us. So there's energy in the dark matter, right? It's oscillating. The mass is equal to energy. And in principle, if you have some sophisticated way, you can build a windmill that will extract the energy from the dark matter. But again, it's a secret. I know it's so crazy that you better not write such a paper at your position right now. I'm allowed.
It's becoming instantly classified.
Yeah.
Ah, shit, the camera. Okay, never mind. Too late now.
I have a maybe naive question to the atomic clock. So the way we define our time relies somehow on the atomic clock. So this should also somehow
yeah, excellent. So you're finding all the things that all the corner that I kind of rounded. So it's true. If you have one clock, you cannot actually distinguish. This is your time, so you cannot distinguish because I folded in the dark matter, right? So indeed, in order to do this experiment, you always need two rulers. You want to have something which does not depend on the dark matter, something which does, and the difference between them will be related to the dark matter. Saying it differently, you always need two systems, and what you can measure is effects which are not cancelled between the two systems. So that's indeed how it really works.
Thanks. Now, just taking you back a little bit, could you explain again the two scales we had for the relaxation, like big F and little f? Where did they come from?
Yeah, right. So we had more than two scales there. So if you watch the master relation of the relaxation was the relation for the stopping condition, V prime equals 0. And this was related to m to the 4th divided by f, roughly equal to v squared, m squared over small f. So for each ensemble of capital F, small f, capital M, and small m, you can get what is the weak scale. Okay? So these are the combination. Now, this required the very weird situation that I have an axion which has two different breaking sources. Let's say in usual axion we have Peccei-Quinn symmetry breaking, which characterized by a scale f. And that's the potential of the axion is controlled by a trigonometric function cosine A over f. Here, in order to realize this, you need two breaking with two different Peccei-Quinn scales, small f and big F. And there should be like exponential relation between them. So this is so much bigger than that. About the capital M and the small m, this is easy because this is like soft breaking of the shift breaking. So that's easy to arrange. So that's how it works.
Okay, yeah, thanks.
So let me ask a bit provocatively. So I want to explain why the weak scale is so small compared to the Planck scale. And we explain it by two scales that are way more apart than the weak scale and the Planck scale. Like, how does that go together that we say, okay, it's still natural to explain a huge mass split by a way larger mass split?
Right, so I totally agree with you. For that, without clockwork, it wouldn't be a complete theory. So the way the clockwork work, just with words, not so not trying to derive the whole thing is basically, what's the fastest way to explain this? It's basically you create a situation where you, are you familiar a little bit with the extra dimension, maybe? Not so much. Anyway, so you create a situation where you have many copies, let's say, of axion. So you have, let's start from the Peccei-Quinn theory. So I'm writing something which has, on this side, I'm writing something which has a U1 global symmetry. So let's write, suppose I'm writing a theory where I have phi dagger phi minus f squared, all of this squared. And I now put a sub-index I here. And capital phi is a complex field. So if I write a theory like that, capital phi will develop a wave, right, of the order of f. And capital phi, because it's a complex field, I can always write it as f plus rho over square root of 2 times e to the I ai. This is for the site I. Over f. And this would be the Goldstone. This would be the axion. Now, I do the same thing everywhere, and I get many axion, n axion, between 1 and site n. Now what I will do is I'm going to add only one more nearest neighborhood coupling. I will write something like phi, capital Phi I, capital Phi I plus 1 cube. Maybe there's conjugate. Yeah, I can do it with the conjugate. It will be easier. OK, once I'm adding this coupling, then I introduce coupling between this nearest neighbor. And now this breaks the individual U1. There's no U1 cross U1 cross U1 cross U1 to the n here, because now I mixed. I coupled this axion theory to that axion theory. OK? But you can easily see that there is still one U1 which is preserved by the whole thing. If I charge this by charge 1, and this charge third, and this by charge 1/3 to the power of n, then the whole thing is invariant by a single U1. Okay, so there's a single axion which is still massless. But because of the relative weight here, you can think about the axion as linear combination of all of these axions. And I want to call it phi because that will be the real axion. Phi is actually equal to sum A over F times basically the Q. In this convention, I think the Q is upstairs. So basically, the linear combination of the U1, which is unbroken by all of the sub-U1s because of the nearest neighborhood coupling, is this weird combination of all the axions. This is the massless guy. And if I will write explicitly the Q, I'll see that it goes like basically sum of A over F times 3 to the I. So there's a massless guy here, which is a linear combination of all the would-be axion here. And it has very small coupling in the end side and very big coupling, order 1, to these sides. You can think about it almost as like the wave function of the would-be axion on this line looks like, I'll do it in yellow so we are not interfering. It looks like exponential shape. Okay, it's something which is very familiar for people who are doing Moose diagram or extra dimension or deconstruction. There are all kinds of words. Maybe for you guys it's all Chinese, so never mind. But there is a very, very easy way to think about such a combination. And now, suppose that this U1, which is linear combination of all, is broken by anomaly here. So that some anomaly here which has a scale capital M. And there's an anomaly here, which is characterized by scale, no, the opposite. Anomaly that is characterized by a scale here, and there's an anomaly which is characterized by a scale here. So this is lambda QCD in one hidden sector here and one here, where under which those QCD, this U1 here and U1 there, are anomalous. So that means that I will generate a potential for this massless, would-be massless axion, and the effective potential once I'm now moving from the A basis to the eigenstate, which is the phi, it will look as if I have a term, two terms to the potential. From the first anomaly, I will just get M to the fourth, let's say cosine phi over F, plus capital M to the fourth cosine phi over F times 3 to the n. So basically, I can identify our capital F as 3 to the n F, and I'm done. Now I need to do some tweaking to make this anomaly depends on the Higgs, but this is easy. And that's it. That's how clockwork works.
It's so much easier when you are deconstructing an extra dimension and just get this result automatically.
Right, right, exactly. I don't know how much experience these guys have, but
extra dimension is for all people stuff. So.
Yeah.
But it is, if you look at it, at that time, people were basically still talking about some ADS and extra dimensions. If you deconstruct a compact extra dimension, you get this immediately. So.
If I understand the string theory people at DZ correctly, you get a shitload of axions for free, basically. And now with having 2 axions, we could solve the Higgs hierarchy.
No,
if we now have more, can we solve even more hierarchy problems, or even like, if we encounter the next hierarchy problem, just search for the one axion model that solves it and then get something in string theory from this?
Well, first of all, you need to be careful because here, the masses of all the other orthogonal linear combinations, so the one massless guy, now you can ask, what is the spectrum of this? Then you can see that, in fact, all the other states are heavy because they pick up a mass from this term, okay? Then the mixed term will give you a term which looks like, you can write it explicitly, it's not that hard. So if I write this plus the Hermitian conjugate, I will get some term which looks like cosine, let's say cosine A1 plus 3 A2 divided by F times times F to the 4th. Yeah. Okay, basically put the VEV and look exactly how the e to the IA appear in this coupling. Okay, so it looks exactly like that. So you see now that this linear combination, after I project the truly massless mode, this linear combination will get a mass of the order of F times lambda. Okay, this lambda needs to be a bit small. Where is this? I didn't put here a coupling, but this should be a bit smaller than 1. So all the other axions pick up a mass of the order of lambda F squared, which is not so small. So when you look at the spectrum, you get one guy which is almost massless, the other one are heavy. So it's not that they can solve more hierarchies. No, they are there just in order to make sure that the orthogonal combination to all of them is massless. In the continuous limit, the spectrum here looks like something which is called a spectrum of linear Dilaton theory. So you have a massless guy, and then at the first level, you have all the other states. It's not like a KK, regular KK spectrum. So I don't think that you can use this to solve hierarchies. What you can get from that is a massless guy, which you can control the periodicity of this guy to exponential level, which is what you need for relaxation. Originally, this was proposed to solve the large field excursion for inflation. That's also a similar, which has a similar problem.
So also like having something similar as the relaxant for the Higgs hierarchy for the cosmological constant problem would be.
That is, so people have tried to use the relaxion, the same mechanism. It goes back even to a paper a long time ago by Abbott. They tried to use relaxation to solve the cosmological constant problem. Typically, it has conflicts with the null theorems. You end up with ghosts, so it doesn't work. It doesn't work for the cosmological constant. Even though there are few attempts, but the bottom line, that's require a very crazy theory. So, no.
Has to do with gravity, or?
Yes, exactly, of course. You need to cancel everything, not only usual problem.
More questions? Okay. Yes.
I have a very simple question. Just what is the back reaction that appears when the Higgs is the first time he's oscillating?
The back reaction is just the jargon for this term. So I can just go back to the slide. So oops. Yeah, so when you write the relaxation potential, the term which has very rapid oscillation, which is proportional to m squared Higgs squared, that is what is called the back reaction term. Okay? So basically it's related to this term, but you need it to depend on the Higgs. So that's the back reaction. It's something that when you go from the symmetric phase to the broken phase of electroweak, suddenly has very rapid oscillation. That's what we call back reaction.
Okay, thanks.
Why do you require the relaxation to stop at the first minimum?
You don't require, you don't have to. But typically what happens is that if it doesn't stop in the first minimum, either it will continue to roll, because each time it's passed through the potential barrier, it's get a little bit.
No? I mean, the barriers get higher, don't they?
The barrier gets higher, but when you do this, you see that it gets some kinetic energy, and now you need to see whether the next barrier is big enough to stop it. But the barriers increase by very little amount, because the reaction is moving by 2 pi f small f, which is tiny, and therefore the Higgs potential increases only by 2 pi small f over capital F. Okay, the way to see it is that if you change f by a small f, then this is not affected, right? Because in one oscillation, this is delta phi is equal to small f, and now if you put here phi plus 2 pi f, then it's suppressed by f over f, and remember that they have exponential relation. So the chain of the vector is very small, so that means that if you jump over the first one, you might actually never stop. You can do this analysis, and it implies that unless you are balancing more carefully the parameter space, it will not stop, even though that there are solutions where it stops much later. I need to be careful about that. So we prefer to assume that it stops in the first one.
So what's the situation with phase transition in this scenario?
Well, it's there. There is phase transition. So there are various ways to think about it. In terms of the Higgs part, because the Higgs is very massive, the electroweak symmetry breaking part is more or less standard, unless the relaxation is heavy, but I'm thinking about a light relaxation. Now, when you start to try to understand what happened to the relaxation potential, because you have this manifold, then we get, we have this huge manifold, and now we're getting into back to all the conceptual problems that we had before. So if you assume that, the inflation ends and there's no probability of tunneling is very small, and you are not in eternal inflations, you are in one patch, then you would see bubble formation and all that. But if you now couple it back, like what we discussed last time, if you couple it back to a landscape where the inflaton, while the inflaton is moving, also the relaxation is moving, maybe relaxation can move backwards, then you get all the usual confusion that we had before. So this is why I prefer to assume that this work, when you factorize, you have the inflation, the landscape sector is decoupled, and then you have only this and nothing else, so you won't have all this complication. But in principle, it could be that you'll have tunneling. Suppose that you go here, maybe you'll have tunneling here. If you are looking at one patch, the tunneling probability is very small. I think someone asked me about this. But if you are subject to eternal inflation, you can jump up and down, then again, you need to calculate it together with the inflaton, and then it's becoming confusing. What we assume here is if the evolution ends here, we actually fine-tune the cosmological constant to be 0 exactly at this point. Okay? It's like entropic, but if the cosmological constant, say, is here, then this means that this will start eternally inflating, and this height is not small, actually. It's of the order of m to the 4th, so it's getting confusing again.
So in particular,
I'm a bit confused by the vacuum structure, so I don't know if the question makes sense, but can you have like a multiple step phase transition in this scenario as well? If you have like, you go maybe in two directions or something?
Yeah, so if you're under the assumption that you're in one patch, then the answer is no. The Higgs mass parameter scale are so heavy that they will not interfere with this. Okay? So the answer is no. I think. I don't think that there was, so this is a young kind of field. I'm not sure that people analyze all the parameter space.
A related question, so,
yes.
But you do ask that, that the classical role, just, so you're trying to avoid the tunneling, right? You have to ask, this is a condition, right?
Yeah, so usually when you assume, if you take the assumption that classical beats quantum,
right,
then the tunneling is suppressed.
Then
yes.
You won't have this. So you have to impose this somehow, avoid.
Right. Apart from this paper that I mentioned by Ann Nelson, and I know that people are working on this now. This is why I'm careful in this reply. Not at Weizmann, but I know that there's a study on this which is about to come out.
So first of all, I want to say you've said already 3 times that the Higgs is very heavy.
Yes.
So this is the opposite of the hierarchy problem. It's great.
Compared to the relaxation, yes.
No, I wanted to, so you've mentioned a couple of times this Dvali idea of, density of states, and
yes.
we never had time to discuss it. Do we have some time to discuss it?
Yeah, so I will give you a superficial answer because I'm not that expert, but what the way he is actually supporting his idea is saying that so if you think about the Higgs mass in the potential, then it behaves as of course as a scalar, right? It's a mass dimension. Now, so how does it work? Let me see. So if you think about two, how does it work? A two form. So we know in QED we have A, which is a one form, and then F mu is the field strength. If you have a two form, then the three form in 4D is trivial. So basically you can think about the coefficient of this as like the three form, which is just trivial, couples to the Higgs. So now, if you don't have branes, if you don't have source of charge, then this is just a trivial theory. But now, if you arrange that there are branes, each time you pass through a brane, it's as if you move from a sector of one topological number to another. So you have a jump in the value here. So you can think about it as mu squared plus something which is topological. It has topological charge, h dagger h. And now how does he do the rest of the story? The rest of the story is that somehow at regions where the sum of this is very small, it looks like you can stack more objects which are charged. He called it branes. So the density, effectively the density of the object that you can charge is related to this sum. So it has an attraction towards a total mass, effective mass equal to 0, because now it's the sum of these two things. And that means that when you look at something which evolve in the landscape, then the density of states will increase when the mass is small. And I don't remember how it couples it to cosmological constant, maybe not. Maybe it's independent for the cosmological constant. Roughly speaking, I think that's his idea.
Thanks.
Any further questions?
By the way, it's the same analogy as the axion, which couples to FF dual, and it's FF dual is trivial because it's a full derivative, but we know that it could be related to topological, so similar to theta term also.
Okay. So I don't see any hands up. So really, I think you guys were lucky. You were exposed to this new exciting frontier in particle physics of the very light and weakly coupled particles. And these amazing cutting-edge experiments that can measure interactions even weaker than the gravitational force. So this is really cutting-edge stuff. And as Gilad was saying, some of this stuff is being actually developed as we speak. So it's really the frontier. So Gilad really did a great job in. Sorry.
No, before you close, I have a question.
You have a question? Okay, sorry. I was closing. So
ask a question because this is simple things. When you just put the plot where there is a little region of dark matter for the relaxation.
Yeah.
So, or I don't know the plot, but maybe you can comment. So there's a region, it's still it's in the natural region for the parameters, right?
Yes, yes.
And then the question is, can you tell us, I don't remember this, but can you tell us, if the abundance that comes out, is there a relationship between the scales and the fact that the abundance comes out in this particular region of parameter space that naturally would explain why the dark matter density is of the order of the baryon density, or it's just happens to be in this region of parameters? Right, I mean, it's about the same order of magnitude, right?
Yes.
So is there anything in the relaxation evolution that will somehow allow you to relate these two, or is this just the place where it works and that's it?
No, I think superficially the way it works, it's dynamical, but you can think about it, it set the misalignment angle for the axion such that you'll get the right relic density. So it's like the axion misalignment. The axion misalignment doesn't know about the baryon density. You just make sure that the initial angle is such that you get now the right relic density. So I don't think that it knows about the baryons.
So it's a bit of a coincidence, basically.
Yeah.
In this
Here
case.
it's
Just
a
like in
coincidence.
thermal dark matter. I
Yes.
guess. Yeah. Okay. Thank you.
Any further questions?
Okay, I'm getting rid of this before we forget.
So let's thank Gilad for this really nice set of lectures.